Alright, welcome back. Today we're going to be looking at Riemann sums and the definite integral. You might remember yesterday we talked about definite integrals, and that was this little integral symbol right here from A to B. We're going to talk about that meaning today, why we write it that way, of f of x dx. And we said all this finds for us is the area under a curve. It's an area finder. Where the derivative finds slope, this finds area. So we're going to take a look at how we can find the area today under a function that is not nice, like a circle or a line, where we can use like formulas from geometry. But we're going to take a look at a random function. So that's what I'm going to draw here. I'm just going to draw some random function. Well, there's my random function, f of x. Now, we want to estimate the area under the graph between the function and the x-axis between the lines x equals a and x equals b. So that's basically just giving us our domain right there. So what we're asked to do today is to find the area on the domain a to b. That's what we're asked to find right here. And from yesterday, you might recall that we drew rectangles, because anytime you see Riemann, you need to think rectangles. Because rectangles are easy. The area is just length times width. We love rectangles. We like Riemann. Riemann! Oh, so yesterday, on our domain from A to B, we would partition the x's, our domain, and we would partition the x's, and we're going to do the same thing here. I'm going to partition it into certain little lengths, preferably all about the same length if we can, but if you can't, that's okay. And I'm going to give these little x values right here. So this might be x sub 1, this will be x sub 2, x sub 3, just to make sure that they have different x values. We also said, okay, so now we're going to draw a rectangle of mathematics. So I want to find the area of just one of these partitions. Remember, Riemann was a way to estimate the area by using rectangles. So if I look at my first graph right here, if I do a right-hand sum from x1 and I move over, I get my first rectangle, the rectangle of mathematics. So there's our first rectangle. Now, it's not the exact area, but it's an approximation. This rectangle approximates the area underneath the function f of x from a to x1. So we have to go and find that area. Well, we know the width of our rectangle. Yesterday we called that delta x. And the height of our rectangle, we use the value at x1 because we use the right-hand rule in this case right here. So to get the value, to get the height of our rectangle, we use the value at x1. So f of x1. And we said to find the area of this lone rectangle, the area of that lone rectangle, that one rectangle, is just going to be f of x1 delta x. And then we would do the same for all of those. Okay? So today we're going to take a look at, well, how do we go from an approximation to the exact area? So let's take a look what we do here. So what the book says to do is we're going to let x equal c sub k. Basically what we're saying is that k on the kth subinterval. For example, x sub 1, x sub 2, x sub 3. We draw the rectangle with the height at that point, which we just did. I don't like to use f of ck, mainly because of, well, obviously, language. So I am going to use my f of x. Alright? So to get the area of our one little tiny rectangle here, we just took the height, f of x. Now we want to keep it generic, so I might call that x sub k, which is what they're going to use, x sub k, times the width of that rectangle, delta x. Now again, if I did my second rectangle, k would be 2. My third rectangle, k would be 3. It's just which rectangle are we looking at. So that's the area for one rectangle. Remember, we get that by length times width. But remember, we have more rectangles, so we're going to add them all up. So to get the sum of all the rectangles, we are going to get that one rectangle, delta x, and then we're going to add them all up. Now you might remember from pre-cal, we use this Greek letter sigma for a sum. It means a summation, where k goes from 1 to n, where n, of course, is the number of rectangles. Nope, can't spell rectangles today. Where n is the number of rectangles. And this right here will add up all the rectangles. So if I let k be 1, my first rectangle, plus if k is 2, my second rectangle, if k is 3, there's my third rectangle. This is what's called a Riemann sum. Riemann, Riemann. That is called a Riemann sum. In other words, this is the summation of the n rectangles. That looks like a sad face. Of n rectangles. So the next question that we want to ask ourselves, well, how do we get the exact area under the curve? And you might be thinking, well, if I want to get the exact area, well, I need to minimize this little error up here. So to do that, well, what if I made more subintervals? What if I made smaller rectangles? Well, if I make smaller rectangles, I am going to get a smaller error up top here. So that's exactly what we're going to do. That's what Riemann said to do. If you want to get the exact area, you just need to add more rectangles. Until something happens. That, well, if we add more rectangles, what's happening to the change in x? So if we add more rectangles, this distance on bottom is getting smaller and smaller and smaller. Well, as this distance is getting smaller and smaller and smaller, that change in the width on the bottom is approaching 0. And that's what we have. So we're going to add more rectangles until delta x approaches 0. And once we do that, we get dx. So this is the definition of what the differential is. dx is delta x going to 0. dx is the smallest change in x. That's what this says. It's the smallest change possible in the x, in the differences of our x's. So in other words, and you might be looking familiar, well, we really can't let delta x ever go to 0, because if we let delta x go to 0, what does that area actually become? 0. So we can't actually let delta x become 0, but we're approaching it. And if you're thinking, man, this sounds like limits, you're exactly right. How we define area is the limit as delta x goes to 0 of our summation formula. K goes from 1 to, we'll talk about that, f of x sub k delta x. But be careful, n is no longer the number of rectangles. Well, if we let delta x go to 0, what we're going to wind up with is an infinite number of rectangles, infinitely thin rectangles. So we let k go from 1 to infinity, which means we're now dealing with an infinite number of rectangles. And at this point, this becomes very difficult to solve, and by some magic, this becomes our definite integral from a to b, f of x dx. And what this equation finds for us is the exact area under the function f of x on the domain a to b. And down here you can kind of again see the definition. It's just our limit process. But I want to kind of go down here. The area bounded by the function and the x-axis is given by this equation. So in other words, if I have a region from A to B and I want to find the area underneath that curve from A to B, this is the integral. This is what we use. It finds the area underneath any function. The exact area, because remember, we're getting an infinite number of rectangles. So we're getting an infinite number of rectangles that are so thin there's zero error between, so there's going to be zero error. It's not going to be an overestimate or an underestimate, it's going to be the exact value. Alright, so if you go to video 2, we're going to take a look at some rules and some examples. I'll see you then. Bye-bye.